Imagine a galaxy shaped like a ripple in a cosmic pond, rings of stars expanding outward like the aftermath of an invisible explosion. Now imagine that galaxy has not one, not two, but 9 perfectly spaced rings. Meet LEDA 13132424, better known as the Bullseye Galaxy, the most elaborate ring galaxy ever discovered. Ring galaxies are rare and complex structures. Among them, the Bullseye Galaxy stands out, not just for its beauty, but for offering critical evidence that could validate decades-old theories of ring formation. In this video, we will explore how ring galaxies form, why the Bullseye is unique, and how its discovery is reshaping our understanding of galaxy evolution. You are watching Planet Spiral. My name is Natalie. Please like this video and subscribe. It really helps me keep bringing you more amazing stories from the universe. Before we dive into the Bullseye Galaxy, let's first explore ring galaxies and their different types. Understanding them will help us see why the Bullseye is truly extraordinary. What are ring galaxies and how were they discovered? Ring galaxies are among the rarest and most captivating structures in the universe, defined by their luminous, circular rings of stars, gas and dust encircling a central core. They stand apart from the more common spiral or elliptical galaxies due to their striking symmetry and unusual morphology. The rings are typically filled with young, blue stars, evidence of intense star formation, while the cores often consist of older stellar populations. Despite their visual appeal, ring galaxies are exceedingly rare. Only around 40,000 have been identified so far. About 1 in every 10,000 galaxies exhibits this peculiar ringed structure. The study of ring galaxies began in the 1940s when Swiss astronomer Fritz Zwicky observed one of the first and most iconic examples, the Cartwheel Galaxy. This galaxy was the first ring galaxy to be studied in detail as a result of a galactic collision. Zwicky proposed that its dramatic ring structure was caused by a high-speed collision in which a smaller galaxy plunged through the center of a larger spiral galaxy. The impact, he theorized, would have generated a powerful shockwave, pushing gas outward and triggering a burst of star formation in a ring. At the time, Zwicky's idea was revolutionary and well ahead of its time, as the tools and data needed to verify such a theory did not exist. However, decades later, advanced observations from the Hubble Space Telescope and the James Webb Space Telescope confirmed his bold hypothesis. Astronomers now believe the Cartwheel Galaxy was once a typical spiral galaxy, transformed when a smaller intruder tore through its core. The resulting shockwave rippled through the galactic disk, compressing gas and forming the luminous outer ring of young, blue stars. Meanwhile, the central region remains turbulent and irregular, a lasting mark of the violent encounter. Another textbook example of a collisional ring galaxy is ARP 147, located about 430 million light-years away in the constellation Cetus. This striking pair of interacting galaxies features a brilliant blue ring formed when a companion galaxy plunged through its center. The resulting shockwave compressed interstellar gas, igniting a burst of star formation along the ring. The blue ring surrounds a reddish core composed of older stars, while the intruding galaxy now shows visible signs of distortion from the collision. ARP 147 offers a vivid demonstration of how such encounters can drastically reshape galactic structure and trigger starbursts. One remarkable example is this galaxy, a stunning system captured by Hubble Space Telescope, where two galaxies are caught in the midst of a dramatic interaction. Their merger has created a luminous ring-like structure that resembles a cosmic embrace, a vivid reminder of the powerful forces shaping the universe. While the collisional ring scenario explains many cases, it does not account for all. Hawke's object, discovered in 1950 by Arthur Hawke, is a nearly perfect ring galaxy with no signs of a recent interaction. Its symmetry and isolation have led astronomers to explore non-collisional formation mechanisms, such as resonance effects or bar-induced dynamics, where the ring forms through internal orbital resonances within the galactic disk. Adding to the diversity are polar ring galaxies, which feature rings of stars and gas orbiting the central galaxy at steep angles, typically perpendicular to the main galactic plane. These structures are believed to arise from galaxy interactions. In one scenario, material from a nearby galaxy is tidally stripped and pulled into orbit around the poles of the hosts. In another, a smaller galaxy collides at a right angle, leaving behind debris that settles into a polar ring. Polar ring galaxies are also part of a wider category of galaxies. Most of them belong to lenticular galaxies category. For example, NGC 2685 is a famous lenticular polar ring galaxy. Same as this, a lenticular galaxy with a rare polar ring structure. Although most polar rings are often found in lenticular galaxies, polar rings have also been observed in elliptical galaxies, broadening the range of possible hosts. The variety of ring galaxies continues to astonish astronomers, revealing just how diverse and dynamic galaxy formations can be. Now we can move into today's focus, Bullseye Galaxy. LEDA 1313424, more widely known as the Bullseye Galaxy, is a striking and unusual ring galaxy located approximately 551 million light-years away in the constellation Pisces. It is currently the most structurally complex ring galaxy ever discovered, exhibiting 9 concentric stellar rings, surpassing all previously known examples, which typically display only 1 to 3. This galaxy is approximately 2.5 times larger than the Milky Way, spanning an immense 250,000 light-years in diameter compared to the Milky Way's 100,000 light-years. Despite its colossal size, it is incredibly faint, far beyond the reach of amateur telescopes and invisible to the naked eye. Only powerful instruments like the Hubble Space Telescope are capable of detecting it. In late 2024, a team at the National Observatory of Japan, using the Subaru telescope, identified a rare triple-ring galaxy with a quite long name, situated roughly 800 million light-years away in the constellation Aquarius. This discovery underscored the scientific value and rarity of multi-ringed galaxies, which are believed to form through galactic collisions. However, the Bullseye Galaxy would soon eclipse this record in both scale and complexity. Bullseye was first noticed in 2019 while examining ground-based imaging surveys when Imad Pasha, a doctoral candidate at Yale University, identified an unusual multi-ring structure. His observation prompted an international collaboration with researchers from Yale, the University of Toronto, and Swinburne University of Technology, who pursued high-resolution follow-up studies. In 2025, the team employed the Hubble Space Telescope's advanced camera for surveys to image the galaxy in detail, detecting 8 distinct rings. Subsequent spectroscopic observations with the Keck Observatory in Hawaii confirmed the presence of a 9th ring, establishing Bullseye as the most ring-rich galaxy ever recorded. In addition to identifying the rings, Pasha made a remarkable connection between the Bullseye structure and a long-standing theoretical prediction. The galaxy's rings appear to have propagated outward almost exactly as models of collisional ring formation had anticipated. This alignment between simulation and observation provided a rare and powerful confirmation of how such galaxies evolve after a central impact. The galaxy's elaborate structure is believed to have formed around 50 million years ago, following a nearly head-on collision with a small blue dwarf galaxy. Traveling at a remarkable speed, estimated between 500 to 2000 km per second, the dwarf galaxy shot through the core of Bullseye in a dramatic cosmic event. The impact acted much like a droplet falling into a still pond. It sent ripples, powerful density waves, radiating outward through the galaxy's disk. While the orbits of individual stars remained mostly undisturbed, these waves gradually caused groups of stars, gas and dust to accumulate over millions of years, forming the galaxy's signature concentric rings. The interaction compressed interstellar gas in rhythmic bursts, triggering waves of star formation that lit up the expanding rings like ripples glowing across the surface of water. Supporting this interpretation, a faint filament of gas still links the two galaxies, detected using the Keck Cosmic Web Imager. The dwarf galaxy, now about 130,000 light-years from Bullseye, shows signs of intense starburst activity, consistent with a violent aftermath of gravitational disruption. Its nearly linear path through the larger galaxy not only stirred matter inward and outward, but also sculpted the distinct radial pattern that makes this galaxy such a compelling galactic bullseye. Because Bullseye is inclined relative to our line of sight, the rings appear unevenly spaced in images. However, simulations suggest that if viewed face on, they would form nearly perfect circles, tightly nested near the core and gradually widening outward. However, the ring structures are not permanent. Simulations indicate that such features typically dissipate over several 100 million years as the wave energy diminishes and the galactic disk stabilizes. Researchers also hypothesize the existence of a 10th, now invisible ring, possibly located 3 times farther out than the 9th, its faintness placing it beyond current detection limits. As the galaxy evolves, astronomers believe it may eventually transition into a giant low-surface brightness spiral galaxy, akin to Malin 1 and NGC 6744. The Bullseye's extended and fading outer rings are consistent with this evolutionary pathway, offering potential insight into how much GLBs may originate from ancient collisional events. Thank you for watching Planet Spiral. Please like this video and subscribe, and I will see you in the next video.